Hello, my name is Peter Verhaaj. In this section, we will look at Java 9 features which help using Java 9 in production. In this section, we will learn about memory management and garbage collection in Java 9, describe different logging systems, and finally review the security and other JVM and runtime enhancements. And this video is about Java 9 garbage collection. We are going to take a look at what is garbage collection in Java generally, the different strategies to collect garbage in Java, and the features of the G1 collector in Java 9. The first question when we are talking about garbage collection is, what is memory management at all? Why do we need memory management? If you look at the history of memory management, then we can separate three eras. The first is assembly machine code programming, very old time. In that time, every memory which was assigned to a process was just available to any machine code, and there were no allocated memory. When we are programming in a higher level language, let's say in C language, it's very typical, then code is allocated and released by the code itself. So the program has to know that it needs memory and has to ask for extra memory. And when it doesn't need it anymore, then it has to release the memory. And if the programmer just forgets to release the memory, then sooner or later, as the program runs in a loop, like a server application for a long time, just loses the memory and it uses up, allocates until the memory runs out and there is no more memory to allocate for the code. Java memory allocation and release of the unused memory is automatic. As it's written on the Sun website, so it's a very old statement, the cost of allocating and collecting memory can play a significant role in how your software performs. The overall memory requirements of your software can have a huge impact on the speed of your program when large RAM requirements force the operating system to use virtual memory. This often occurs when memory is allocated but not properly released. Although the JVM is responsible for freeing unused memory, you have to make it clear what is unused. To write successful large-scale programs, you need to understand the basic of the garbage collection mechanism. So this is the reason why we have to know garbage collection, not because we want to write garbage collection algorithm, but because we have to understand how it works when something is not optimal, when we have to tune it a little bit, when we have to care about what we really allocate, what we really do with objects. To care sometimes, which almost always automatic in nowadays programs in Java, if we don't use an object anymore, then we have to make it unreachable, as we will see later what it means. We don't need to deallocate it, and the objects usually by the program code become unreachable without paying attention to that. Sometimes a little bit later than it could be, but it's okay. But if there is a performance issue, then we have to pay attention to that, and then we have to know what to pay attention to. What we have to know about object lifecycle: we don't allocate memory, we create objects, and the memory is automatically allocated, which is needed by the objects. First, an object is created. This is when we issue the new operator. Then it is in use. It's so-called strongly reachable. The strongly means that there are other reachabilities like soft and weak reachable or phantom reachable, but we won't go into the details of that because now we are focusing on garbage collection. After a while, the object may become invisible and then unreachable then it gets collected by the garbage collector. It may get finalized, and finally it's deallocated. The memory for the objects are allocated on the heap, and the local variables are on the stack. And when we return from a method, then a part of the stack which was allocated for the local variables of that method is automatically released. The stack pointer goes up and down, but the heap, the objects on the heap, have to be recollected. So the garbage collection reclaims the memory space which were allocated for objects and which are not reachable anymore. When we are programming in Java, then programmers focus on the business code and memory management is up to the JVM. The heap is just memory that the JVM gets from the operating system. It's nothing mystic. The default size is usually small. And if we started a JVM and we configured it, it's no way to increase it afterwards. But we can control the size of using the command line options minus capital X and MX, MS and MN, which is the size, the minimum and the maximum value. But we cannot tune these values. The actual heap can increase and decrease its size, calling the operating system between MX and MN, but not above that or below that. When we talk about the garbage collection, it's very important to mention that there is no standard Java garbage collection. The Java standard itself, so the language, does not specify how garbage collection should work. The different Java virtual machines implement different garbage collection algorithms. And there are more than 20 different JVM implementations. So when we are talking about Java 9 and G1, then we are not talking about the Java language, but we talk about the reference implementation from Oracle. And then let's talk a little bit about the garbage collection itself. So the very basic things of garbage collection. The first step in garbage collection is to mark all objects reachable from the references that are on the stacks of living threads. So if I have somewhere a local variable in the actual method in one of the threads, or somewhere above a local variable that is currently not the actually running method, but it was calling the actual method, or even above that, then that object is marked because it's reachable. We have a local variable pointing to it, so we may need it. Then also mark all the objects that are reachable from class static fields, which are loaded and not yet purged, so that classes are still alive. And also objects which are referenced from Java native interface modules. If we have any native interface which is written in C language and can work together with the JVM. And this marking is transitive. So if I marked an object and this object uses another object, then that object is also still in use. And if that reference is another, then we go on and on until we mark all the objects that are reachable this way. After we are done with this marking, then we can say that any object that is not marked is free. It should be collected. So we collect them as free memory. And after that, we have objects which are not continuously one after the other in the memory, but there are gaps between, and therefore we rearrange these objects. The garbage collector rearranges these objects in the memory so that there is a continuous memory allocated for all the objects, but at the same time the free memory becomes again continuous. So it may not happen that we need, let's say, 100 bytes somewhere in the memory, and we have 300 bytes, but we have it 5 times 20 bytes, and we cannot allocate a 100 bytes object. It may happen if the memory is segmented. These are the 3 major steps of garbage collection. Garbage collection assumes, based on statistics, that most objects die soon. Most of the objects that we create doesn't have a long life. But after a while, if an object reaches some certain lifetime, then they stay usually long. This is just something that usually programs do, without that the programmer is paying attention to that or something like that. And it's also an experiment, and we see that in usual programs, old objects do not care about the new object. There is hardly ever reference from an old object to a new object. Now, it may happen that we have something like an object cache, which is an old object because it stays there for a long time, and then it references newly created objects. But it also means that garbage collectors may have hard time using such a pattern. But based on this, what we see usually in programs, Java garbage collector separates the heap into 3 main areas. Young generation for new and relatively young objects, old generation for objects which reached certain lifetime, and permanent generation for class objects that never die, which is not really true because with modern dynamic languages they generate a lot of classes which are just short-living. Therefore, G1 garbage collector doesn't have permanent generation, it just has young generation and old generation, but we will look at that later. It's still good to know that permanent generation exists in Java 8, 6, 5, and so on in the old Javas. For a few years we may still face permanent generation issues. The different garbage collectors that are available even in Java 9, different collectors are there, it's just that the garbage first collector is the first one, the default one. But these collectors are serial garbage collector, parallel garbage collector, concurrent mark and sweep garbage collector, and garbage first GC G1, which we will talk a little bit at later. But to understand that, we have to look at first the simple one, the oldest one, the serial, then the parallel, then the for long time ruling one, the concurrent mark and sweep, and then we will talk about the advantages of the G1 garbage collector. The serial garbage collector is very simple. The different threads from the left to right, as we can see, run. Then when there is not enough memory, so there is a threshold that memory starts to be occupied, and the garbage collector, the GVM, feels that it has to collect the unused objects, stops all the threads, then the garbage collection is done, and when it's finished, then garbage collection runs on. Then the program runs on, and then it runs until again garbage collection should start, then it collects, and so on. The difference between this one and the parallel garbage collection is very simple. Parallel garbage collection implements an algorithm where the marking and the sweeping and everything runs in multiple threads. The clear advantage is that if we have multiple processors, multiple cores, then this is faster than the simple garbage collection. The concurrent mark and sweep is a little bit different, because when it needs garbage collection, then it stops all the threads, then makes an initial marking, and then it says that, okay, we made some marking, we are not finished yet, but based on what we have done, we can mark other code, other objects. So let the threads run on, program works on, and while the program threads run on a few threads, marking garbage collection parallel with the application threads makes further marking. And when it's done, there is a remarking step, and then the sweeping is done parallel with the other application threads. So the initial mark actually is the so-called stop the world action. It stops the Java threads, and if it's a server application, then everything stops for the initial mark phase. If we have an HTTP request, then the server is not answering for that while. Then it marks all the objects which are reachable directly from outside of the old generation, young generation, stack, and so on. And then the world rolls on. This is the initial part, which was on the left side of the screen. Then it does the concurrent mark and pre-cleaning, marks all the objects which are reachable transitively, and then marks all objects based on changes that happened just during this phase. And for that, it has a very fast algorithm, but it's very obvious to know that because, for example, if we imagine that we are searched for a piece of paper, a group of people, and I am having this paper in my hand, and you want to find this paper and you can ask me if I have it in my hand. And then you ask somebody else, but in the meantime, in another thread, as an application program, I can hand it over to someone. Then it may happen that you ask my friend, he doesn't have the paper, then you come to me, in the meantime I give the paper to my friend, and I say, no, I also do not have this piece of paper, and then you think that this piece of paper can be collected. No, it cannot, because it was in my hand while you were not asking me, and it was in my friend's hand when you were asking me. So you don't find it. There should be a final marking phase. This is the remarking, and it can only be done if we stop the world again. Otherwise, you just made this piece of paper we handing each other playing the cat's play. You cannot catch it while we are throwing the paper to each other. But if we cannot throw it, you just can find it very fast, and then you can mark it as reachable. And in this phase, it goes parallel, and then it does a concurrent sweeping, compacting the memory. The G1 garbage collector is a little bit different in that there is no fixed size young-old generation, like in the old, or let's say not that old, but older garbage collection. But the heap is partitioned into heap regions. And the G1 collector and memory management generally assigns role to regions as needed. So if, while it may have happened that there was not enough memory in the young generation, and therefore there were some objects which were not that old, but were the oldest in the young generation, and there was not enough space for other objects, and therefore they were prematurely tenured and moved into the old generation, and it was not good. In G1, it doesn't happen, because if something like that would happen, then G1 just says that, hey, I need more young generation out of the total heap, and it just assigns more young generation role to some regions. The other thing is that it first collects those partitions which are almost empty, because it can be done very fast. And then it can just generate free memory very fast. And it's also a very important thing that it tries to reach a given and command line specifiable target post time. It's also very important to note that this is not a real-time garbage collection. It may not reach this target. It may happen that I specify that the maximum post time my server can live with is 10 milliseconds, and the G1 garbage collector, because of the nature of my program, just stops my program for 20 milliseconds or even more. There is no guarantee. But based on statistics, what it experienced before and some other calculation, it tries to reach this target post time, and usually it does. When we want to decide and be happy that we want to use G1, maybe not. It very much depends on what we want to reach. So what is important for us? If I have an offline calculation, which is like a numerical calculation, which usually we don't use Java for that, but it may happen, and I run it on some machine and I leave it there for all the night, so it runs and runs and runs. What I'm interested in is the total time it is running until it finishes the calculation. My algorithm and the processor speed just gives the time. But there is also some time spent with garbage collection, and I want the time spent with garbage collection to be minimal for the whole running of the program. So in that case, the overhead, the throughput of the garbage collection is important. The time spent by collecting the garbage divided by the total time should be minimal. The second is more important for server application, the maximum pause time. The time the garbage collection stops the word, because during that time my server doesn't answer the requests. And I want to minimize it, and I don't care if this algorithm and this tuning just spans twice as much CPU cycles as the serial garbage collector. I don't mind, because I have enough CPU, I have power, it can run. I just don't want my program stopping, hanging, lagging, because user experience is the most important for me. Then it may be that frequency, how often garbage collection runs, may be important. Or it may be important if I'm short in memory, like in a mobile phone or something where the memory is not that abundant, then the memory footprint needed for the garbage collection, because garbage collection itself also needs memory to manage its own structures. Maybe that's important and it's not that big. And it also may be important how promptness, how promptly an object is collected after it's not used anymore. Java 9, the new thing in Java 9 is that it uses the G1 garbage collector by default. For that there are two major reasons. One reason is that this algorithm became mature. A lot of bugs were discovered since it was first available in Java. The other thing is that if we look at Java 20 years ago and now, then the processor architectures are totally different. Now everybody has multiple cores. Even on my machine I have 4 CPU cores, and each is capable of running 2 threads, so it's like it's running 8 threads at a time, and it's just a notebook. 20 years ago we had something like 150 megahertz CPUs, single core, very limited onboard cache and things like that, so it's totally different architecture. G1 was already available in Java 6 update 20 as an experimental. Since Java 7 update 4, it's generally available, and it was selectable using some extra options like XX, use G1's GC. And in Java 9, it's the default garbage collection algorithm. And there are some options, for example, max garbage collection pose millis, where I can specify the maximum milliseconds I desire, not guaranteed, I desire only, that the garbage collector shouldn't pose more than, in this case, 200 milliseconds on the GVM. And I can also fine-tune the heap occupancy percent. So if 45% of the total heap memory is already occupied, then I want a garbage collection event occur and start collecting the garbage. Garbage collection is very complex and very detailed, and there are a lot of things, a whole book worth of things about garbage collection, how G1 works. So even though it's a very long video, almost half an hour, it just scratches the surface of garbage collection. But it's important to know at least some of these things to understand a little bit what it is. And this video is actually a good base to understand and get a feeling and to know what to look at after, if you really are interested in more details about garbage collection.